Java bytecode is the instruction set of the Java virtual machine. Each bytecode is composed by one, or in some cases two, bytes that represent the instruction, along with 0 or more bytes for passing parameters. Of the 255 possible byte-long opcodes, 198 are currently in use, 54 are reserved for future use, and 3 instructions are set aside as permanently unimplemented. Note that the Java bytecode system does not directly support floating-point operations beyond 32 bits, except indirectly via bytecodes that enable the use of 64-bit and 80-bit intermediate i.e. floating-point maths. Relation to Java: a Java programmer does not need to be aware of or understand Java bytecode at all. However, as suggested in the IBM Developer Works journal, understanding bytecode and what bytecode is likely to be generated by a Java compiler helps the Java programmer in the same way that knowledge of assembly helps the C or C++ programmer. Instructions fall into a number of broad groups: load and store, arithmetic and logic, type conversion, object creation and manipulation, operand stack management, control transfer, method invocation and return. There are also a few instructions for a number of more specialized tasks such as exception throwing, synchronization, etc. Many instructions have prefixes and/or suffixes referring to the types of operands they operate on. These are as follows: for example, iadd will add 2 integers, while dadd will add 2 doubles. The const, load, and store instructions may also take a suffix of the form n, where n is a number from 0 3 for load and store. The maximum n for const differs by type. The const instructions push a value of the specified type onto the stack. For example, iconst5 will push an integer 5, while dconst1 will push a double 1. There is also an occurrence null, which pushes null. The n for the load and store instructions specifies the location in the variable table to load from or store to. The load0 instruction pushes the object in variable 0 onto the stack. Store1 stores the integer on the top of the stack into variable 1. For variables with higher numbers, the suffix is dropped and operands must be used. Example: consider the following Java code. A Java compiler might translate the Java code above into bytecode as follows, assuming the above was put in a method. 0, iconst2, 1, store1, 2, iload1, 3, sipush 1000, 6, if I see mpge 44, 9, iconst2, 10, store2, 11, iload2, 12, iload1, 13, if I see mpge 31, 16, iload1, 17, iload2, 18, erm, 19, ifn 25, 22, goto 38, 25, ing2, 1, 28, goto 11, 31, get static number 84. Field Java system out, Java print stream. 34, iload1, 35, invoke a virtual number 85. Method Java print stream println, I, v, 38, ing1, 1, 41, goto 2, 44, return. Generation. The most common language targeting Java virtual machine by producing Java bytecode is Java. Originally only one compiler existed, the JAVAC compiler from Sun Microsystems, which compiles Java source code to Java bytecode. But because all the specifications for Java bytecode are now available, other parties have supplied compilers that produce Java bytecode. Examples of other compilers include JIX, compiles from Java to Java bytecode, Espresso, compiles from Java to Java bytecode, GCJ, the GNU compiler for Java, compiles from Java to Java bytecode. It is also able to compile to native machine code and is available as part of the GNU compiler collection. Some projects provide Java assemblers to enable write-in Java bytecode by hand. Assembly code may be also generated by machine, for example by a compiler targeting a Java virtual machine. Notable Java assemblers include Jasmine, takes textual descriptions for Java classes, written in a simple assembly-like syntax using Java virtual machine instruction set and generates a Java class file, Jamaica, a macro assembly language for the Java virtual machine. Java syntax is used for class or interface definition. Method bodies are specified using bytecode instructions. Krakatau currently contains 3 tools, a decompiler and disassembler for Java class files and an assembler to create class files. Lilac, an assembler and disassembler for the Java virtual machine. Others have developed compilers, for different programming languages, in order to target the Java virtual machine, such as Cold Fusion, JRUBY and Jthon, 2 scripting languages based on Ruby and Python, Groovy, a scripting language based on Java, Scala, a type-safe general-purpose programming language supporting object-oriented and functional programming, JGNAT and AppletMagic, compiled from the Ada programming language to Java bytecode, C to Java bytecode compilers, Clojure, a functional, immutable, general-purpose programming language in the Lisp family with a strong emphasis on concurrency, Midlet Pascal, JavaFX script code is also compiled to Java bytecode, Kotlin. Execution, there are several machines available today, both free and commercial products. If executing Java bytecode in a Java virtual machine is not desirable, a developer can also compile Java source code or Java bytecode directly to native machine code with tools such as the GNU compiler for Java. Some processors can execute Java bytecode natively. Such processors are known as Java processors. Support for dynamic languages. The Java virtual machine provides some support for dynamically typed languages. Most of the existing JVM instruction set is statically typed, in the sense that method calls have their signatures type-checked at compile time, without a mechanism to defer this decision to run time, or to choose the method dispatch by an alternative approach. JS 292 added a new invoker dynamic instruction at the JVM level, to allow method invocation relying on dynamic type checking. The DaVinci machine is a prototype virtual machine implementation that hosts JVM extensions aimed at supporting dynamic languages. All JVMs supporting JSE7 also include the invoker dynamic opcode. See also Java bytecode instruction listings, Java class file, list of JVM languages, Java backporting tools, C to Java virtual machine compilers, JSTIK, Common Intermediate Language, Microsoft's rival to Java bytecode, Object Web ASM. References. External links, Oracle's Java Virtual Machine Specification, Programming Languages for the Java Virtual Machine, Bytecode Visualizer bytecode Viewer and Debugger, Adapt JStack Trace bytecode level debugging with a full control of the stack, the local variables, and the execution flow, Java Class Unpacker plugin for Total Commander, it lets open class files as compressed archives and see fields and methods as files. The bytecode can be viewed as text using F3.